By now you know that logic is the science of rational argument. When you study logic, you must try to acquire two main objectives. The first one is to learn how to analyze a given argument and determine whether that argument is in rational form or not. The second objective is learning how to construct rational arguments. So these are the two main objectives that you try to achieve when you are studying logic. In order to achieve these two objectives, you must study arguments to a certain depth. Therefore, one of the first things that we have to do is to find out what arguments are made of. What are they composed of? Arguments are constructed using building blocks called propositions. Then comes the big question, what are propositions? Let us find out. In everyday life, we express what originates within our minds in four different ways. Through speech, through writing, through gestures, and through deeds. These are the four different ways we express what originates within our minds. As students of math, we are not really interested in deeds and gestures. So we will mainly focus on verbal and written expressions. We can broadly categorize the verbal and written expressions into four different groups. The first group is called declarations or statements. These are basically our opinions about the things that we come across. A declaration is basically an opinion about something or someone. For example, roses are red, violets are blue, 57 is not a prime number. These are all declarations or statements. The second group is called questions. When we want to know something, we ask questions. For example, what is the tallest building in New York City? Did you do your homework? These are all questions. The third group is called commands or requests. When we want to get something done, we use commands or requests. Rodney, sit down. Please give me that thing. These are all commands. The fourth group is called exclamations. When we want to express a strong emotion, we use exclamations. Oh my God! Oh wow! These are all exclamations. Now I am going to introduce you to a new concept called truth value. Let's see what is meant by truth value. Truth value. What is truth value? We say a verbal or a written expression has a truth value if it is either true or false. It can never be both, right? So if a verbal or a written expression is true or false, we say that expression has a truth value. So first we will go to exclamations. Oh my God! Can you say oh my God is true? No. Can you say oh my God is false? No. So it seems exclamations do not have truth values. How about commands? Rodney, sit down. Can you say it is true? No. Can you say it's false? No. What about questions? Did you do your homework? Is it true? No. We are just asking a question. Is it false? No. So, questions, commands and exclamations do not have a truth value. How about declarations or statements? Roses are red. Yeah, some roses are red. It's true. Violets are blue. Yeah, true. 57 is a prime number. False. 57 is not a prime number. Declarations have truth values. They can be either true or false. But do all declarations have truth values? Let's find out. Now, you're having a chat with somebody and he says, I am lying now. I am lying now. Now, this is clearly a statement. He's saying he's lying now. I am lying now. Okay? Can you say that it is a true statement? It can't be, because if this is true, then he cannot be lying now. Because if this is true, it contradicts what he is saying, because he is lying now. He cannot be saying the truth. So it must be false. If it is false, if what he is saying is false, it means he is telling the truth. So such statements are called paradoxes. This is a paradox. It's actually called liar's paradox. Declarations such as these do not have a truth value. We cannot assign a truth value to a statement like this. So all declarations do not have truth values, but most declarations do. Now we come to the formal definition of a proposition. So this is the formal definition of a proposition. A proposition is a declaration which has a truth value. So a proposition can be either true or false. A proposition can never be both true and false. It can be either true or false. This is what is meant by a proposition. So that is the answer to our question. Based on the complexity, we can divide propositions into two types: atomic propositions and compound propositions. Propositions which cannot be broken down into or reduced into more simpler propositions are called atomic propositions. Propositions that cannot be broken down into or reduced into more simpler propositions are called atomic propositions. We use these atomic propositions to construct more complex propositions called compound propositions. Compound propositions. Okay, so now we have two main types based on the complexity: atomic propositions, or the atoms of propositions, and the compound propositions. There are two main ways that we can use atomic propositions to create compound propositions. Mind you, when we speak or when we write, we do this subconsciously. Let's see how this is done. We use certain words called logic connectors. Logic connectors. Connectors or logic operators to convert or connect atomic propositions into compound propositions. Logic connectors or operators. These are the 5 main logic connectors. First one is not, second one is and, third one is or, fourth one is if, then, fifth one is if and only if. There is a 6th logic connector called exclusive OR. We will look at exclusive OR when we are constructing truth tables in the next video. So these are the 5 logic connectors. The compound propositions that we create using NOT are called negations. The compound propositions that we create using NOT are called negations. The compound propositions using AND are called conjunctions. Conjunctions. Compound propositions constructed using OR are called disjunctions. Disjunctions. Those constructed using if-then are called unidirectional implications. Implications. Those constructed using if and only if are called bidirectional implications. Bidirectional implications. So you can see that there are 5 main types of compound propositions, right? So those created using NOT are called negations. Then we come to conjunctions, disjunctions, unidirectional implications and bidirectional implications. These are the 5 main logic connectors. These are the 5 different types of compound propositions constructed using each of these logic connectors. Now we are going to study each of these 5 types of compound propositions. First, the negations. Now look at these 2 examples. The first one is pi is not a real number. Second one is Gauss was not a musician. The first one, pi is not a real number, was constructed by the atomic proposition pi is a real number. That is the atomic proposition. Using the logic connector NOT, we have constructed a negation. When we consider the second negation, it is constructed by the atomic proposition Gauss was a musician. Using NOT, we have constructed the negation. Looking closely, you can see that the logic connector NOT is capable of converting a single atomic proposition to a compound proposition. It does not need 2 atomic propositions. It can convert a single atomic proposition to a compound proposition. Therefore, we call the logic connector NOT a unary logic connector, a unary logic connector, right, or a unary logic operator. The other 4 logic connectors or logic operators need 2 atomic propositions to construct compound propositions. Okay, so they are called binary logic connectors or logic operators. Okay, so this is something that you must know. Now, just like in algebra, in logic we do not like to use words. We prefer things in symbolic form, right? So the symbol that we use to represent not is something like this. This is the symbol that we use to represent not. Now, you know that in algebra we use lowercase letters such as x, y and z to represent variable numbers. Same way, we use lowercase letters such as p, q and r to represent different propositions. So when we want to express the negation of any atomic proposition, we write it like this, right? Because P can be any atomic proposition, right? So this means not P. Okay, if P is pi is a real number, then this means pi is not a real number. If Q represents Gauss was a musician, then this means Gauss was not a musician. Okay, I hope you understand. Next we are going to look at conjunctions. The first example is Mozart is a mathematician and a politician. The second example is Chanakya was a strategist and an advisor to the king. These are 2 conjunctions. Now the first conjunction was created by 2 atomic propositions. Mozart is a mathematician, that is the first atomic proposition. The second atomic proposition is Mozart is a politician. We have connected those 2 atomic propositions together using the word and. Now in the second example, we have used 2 atomic propositions to construct this conjunction. What are those 2 atomic propositions? Chanakya was a strategist and Chanakya was an advisor to the king. Using and, we have connected those 2 atomic propositions to construct this conjunction. Chanakya was a strategist and an advisor to the king. Now the symbol for N is something like this, like the inverted V. So when we write like this, it means P and Q, where P can be one atomic proposition and Q is another atomic proposition. So this is how we depict a conjunction when we write logic. Then we come to disjunctions. Now we have used the same examples as in the conjunctions. The first one is Mozart is a mathematician or a politician. Second one is Chanakya was a strategist or an advisor to the king. Now in the first example, we have used 2 atomic propositions. Mozart is a mathematician and Mozart is a politician. We have used the logic connector or to connect the 2 to create a disjunction. In the second one, Chanakya was a strategist is the first atomic proposition. Chanakya was an advisor to the king is the second atomic proposition. We have used the logic connector or to construct the disjunction. Chanakya was a strategist or an advisor to the king. Now the symbol for disjunction is like this, like the V. So when we write like this, it means the disjunction P or Q. This is how we depict a disjunction when we write logic. Now we have come to unidirectional implications. Now I told you that unidirectional implications are compound propositions that are constructed by using the logic connector if-then. So let us look at two examples. The first example is, if 18 is an even number, then it is divisible by 2. So what are the atomic propositions? 18 is an even number is the first atomic proposition, and the second atomic proposition is 18 is divisible by 2. By using if then, we have constructed this compound proposition. If 18 is an even number, then it is divisible by 2. Let's look at the second example. The two atomic propositions are, Ricky is in art school. The second one is, Ricky is good at painting. Using if then, we have constructed this unidirectional implication. If Rick is in art school, then he is good at painting. Now the atomic proposition which immediately follows if is given the honorary term antecedent, and the atomic proposition which immediately follows then is called the consequent. So this is, the first example, this is the antecedent. The second one is the consequent. In the second example, this is the antecedent. Rick is in art school is the antecedent. Rick is good at painting is the consequent. Okay? Now don't worry about these new terms, conjunctions, disjunctions, unidirectional implications, this and that. Don't worry about that. Just try to get hold of the concept behind them. Okay? Now we use this symbol, an arrow from left to right, to represent if then. So when we write like this, it means if P then Q, or P implies Q. If P then Q, or P implies Q. Okay? Now here P and Q are any two different atomic propositions. Okay? This means if P then Q, or P implies Q. Now I am going to tell you a joke. It's a joke, right? It is said that somebody knows his math well if he knows these two things. The first one is, he knows how to pronounce this name properly. The second one is, he knows the true meaning of if and only if. It's a joke, right? So we have come to the last type of compound propositions called bidirectional implications. Look at this example. Richard is an alcoholic if and only if he consumes 2 bottles per day. Do you know what this means? This means if Richard is an alcoholic, then he consumes 2 bottles per day. And if Richard consumes 2 bottles per day, then Richard is an alcoholic. It's the combination of 2 unidirectional implications. Okay? The first one is from left to right and the other one is from right to left. The symbol that we use to represent if and only if is a bidirectional arrow. So when we write like this, it means P if and only if Q. This is equal to the conjunction P implies Q and Q implies P. That's what it means. Now, lot of students of math do not have a proper understanding of this concept. So, when they are asked to prove a statement involving if and only if, they prove most of the time only this. So, they only get 50% of marks. So, when they are asked to prove a statement involving if and only if, they must prove both this and this. Then they will get full marks, because the conjunction of P implies Q and Q implies P is called P if and only if Q. Now these are the 5 main types of compound propositions that you must know. Next we come to a concept called order of precedence. Let's see what it means. Now, if you come across something like this, what does it mean? You know that there is a negation here and there is a conjunction here. Which of these operations should be considered first? Is it the negation or the conjunction? Now, if you consider negation first, we will conceive this as, this means the conjunction of not P and Q. Okay? If you consider the conjunction first, you would conceive this as the negation of the conjunction P and Q. Which is correct? This is confusing, right? Because you might get 2 different ideas if there is no rule regarding precedence of logic operations. There is a rule, luckily. By convention, we say that negation precedes or done before conjunction, and conjunction precedes disjunction, precedes unidirectional implication, precedes bidirectional implications. Now there is this rule. Because of this rule, we know what this means. Now, we have to consider negation first. There are 2 operations we have to consider negation first. So, what it really means is that this is the conjunction of not P and Q. This is what it means. This is the correct interpretation, not this. This interpretation is wrong. This interpretation is wrong. Here, the negation is performed before the conjunction. Here, the conjunction is performed before the negation. Okay? So, this is the correct interpretation if you write like this. This is the wrong interpretation of this. Now, you must know something important. Just like in algebra, a parenthesis will always override the precedence. So, if you want to write the negation of the conjunction P and Q, you have to always use a parenthesis like this. This does not mean this. This means you don't have to write a parenthesis here actually, because you always know that not P, the negation is performed before the conjunctions. So if you know the order of precedence, you know that this means the conjunction of not P and Q, not the negation of P and Q. If you want to write the negation of P and Q, you write it like this. So if you want to depict the negation of the conjunction P and Q, you include the conjunction within the parenthesis, okay, because parenthesis overrides precedence, right? So that is what is meant by order of precedence. Now before I wind up, I want to tell you something important. The truth value of a compound proposition depends on two factors. The first one is the truth value of its component atomic propositions. That is the first factor which determines the truth value of the compound proposition. The second one is the type of logic connector that is being used to construct that compound proposition, because there is a rule that is that involves each of these logic connectors, right, which determines the overall truth value of the compound proposition. So in the next video we will study about how the truth value of a compound proposition varies with that of the truth values of its atomic propositions and the logic connector that is being used to construct that compound proposition. Thank you for watching.